So our speaker now is Pham, who will speak about additive combinatorics from probabilistic and combinatorial perspectives. So we will have a 1 hour talk, and then there will be a 5-minute break before the next talk. Okay.
First I'd like to thank for the invitation to this year's Chern-Weil Symposium, and it's been a really nice event so far. So in this talk, I plan to tell you about several questions in additive combinatorics. But quite surprisingly, the main message in our approach is that to tackle these problems, we can at times forget almost everything about addition and about the group structure, and instead view the problems from a broader, more general combinatorial perspective. So hopefully by the end, this message will become clearer to you. Now to start, let me tell you about one of the most fundamental notions in additive combinatorics, and that's a sumset. And in Larry's talk earlier, we saw a very close cousin of the sumset, which is a different set. Well, to start, let's let G be an abelian group. For a finite subset A of G, we'll define the subset A plus A. This is simply the collection of all elements of the form A plus B, where A and B are elements of A. Later on in the talk, we'll see other variants like the different set and also generalizations of this notion to non-abelian groups. But I'll tell you more about these as we get there. Now let me also define this P parameter that we call the doubling, denoted by Ka, and this is simply the ratio of the size of the sumset A plus A over the size of A. So one of the most fundamental questions in additive combinatorics is the following. What can we say about sets A that have the small doubling, that have doubling Ka bounded above by some parameter K? So to start the investigation, let's revisit one of the most classical setups in additive combinatorics. So when the group G is the group of integers. So given a set A of integers, it is an easy exercise to show that the size of the sumset A plus A is always at least twice the size of A minus 1. And equality here can only occur if and only if A is extremely structured. So if A is an arithmetic progression. On the other end, if A has no structure whatsoever, then the size of the sumset A plus A can be as large as A plus 1 choose 2, so roughly quadratic in the size of the set A. And so we see here that for an integer set A, the doubling K can range between roughly 2 and linear in the size of the set A. And we will see that the smaller the doubling is, the more structure that we see in the set A. So for now, let's try to see if there are more interesting examples other than the progression of sets A that have doubling bounded above by some constant. And there's indeed a general class of these. So let me introduce the generalized arithmetic progression, or gap of some dimension D. Here's this formula on the slide, but you can ignore that. We can just think about a generalized arithmetic progression of dimension D as what you get by starting from a box in D dimension, and then take a linear projection to map that box back to the integer axis. So here's a gap of dimension 2. If we add the box to itself, then roughly each of the side lengths will at most double, so the volume of the box would grow by a factor that is at most 2 to the D. And likewise, you can show that if you take a gap of dimension D, then its doubling will be bounded above by some constant depending only on D. So if we now go back to this question, we now know a large class of examples of sets A whose doubling is bounded above by some constant. In particular, dense subsets of generalized arithmetic progression with some bounded dimension D. We can ask, other than these obvious examples, are there more complicated sets A whose doubling is bounded above by a constant? And the remarkable theorem of Freiman tells us that the answer is essentially no, at least qualitatively. So Freiman proved that if we have an integer set A with doubling at most K, then A must be a dense subset of a generalized arithmetic progression P whose dimension D is bounded as a function of only the doubling parameter K. Now, if you think about K as being a fixed constant and the size of the set A is going to infinity, then Freiman's theorem is a quite satisfying answer to the motivating question that we have above. However, as you send the parameter K to grow as the size of the set A grows, then quantitative aspects of Freiman's theorem is still not completely understood. It remains one of the important questions. So here by quantitative aspects, I mean what is the correct dependency on the parameter K of the quantities that appear in the theorem. So the dimension D and the density of the set A inside the generalized arithmetic progression P. And I won't go into too much detail. Let me just mention that the proof of Freiman's theorem There are several proofs of this. And one of the very influential proofs is actually an alternative proof by Rouger in the 90s. And this proof is following mostly an analytic approach, so using Fourier analysis and together with other important ideas like the Rouger's modeling and covering lemmas. Now, Freiman's theorem is one of several results that all go along this important theme in additive combinatorics, where we want to associate to a set A that has small doubling certain notion of structure. And as in the case of Freiman's theorem, in many cases we want to say that A is dense inside some globally structured object. And these type of results have many influential applications across math and computer science. So for instance, random matrix theory, some product estimates which have application to discrete geometry and harmonic analysis. And there are important applications in theoretical computer science around property testings and so on. I will not list all of these exhaustively. But on the other hand, there are several drawbacks to these type of results. So in particular, many of them come with a weak quantitative dependence on the parameter k, and they would only tell us some non-trivial information if the parameter k is small compared to the size of the set A. Now, if we revisit the possible range of the doubling, we actually know that as soon as the doubling parameter k becomes small relative to A, so as soon as k becomes little o of the size of A, then already we expect to see a lot of additive structure inside the set A. And there are indeed applications, as we shall see, where it will be important to capture the additive structure of A as soon as the doubling becomes small relative to A. And so in this talk, we'll see some of these applications, and they will also motivate us to look a little bit more broadly at our notions of structure for the set. So in particular, we'll consider these three notions of structure. The first one is an explicit notion of structure, where Freiman's theorem, for example, is a prototypical case. We'll also consider a more statistical notion of structure, where we want to say that sets A with small doubling are very special in the sense that there are very few of them. And the last notion, I will call it probabilistic or information theoretic. In this case, we want to say that the sumsets A plus A of sets A with small doubling can be well approximated by using very few random bits. Together with these different notions, another common aspect of all the results I will discuss later is that they all follow an approach that is overarchingly combinatorial. So many times we will forget almost everything about the group structure involved in the problem, and we'll move to a very general graph theoretic representation of the problem. We'll also make frequent use of probabilistic ideas, so we use randomness to probe and to study the structure of the sets with small doubling. Okay, so with that, this is my rough plan for the rest of the talk. We'll have roughly 3 chapters corresponding to these 3 notions of structure. We'll start with a result that is about the explicit structure of sets with small doubling, and we'll go towards a conjecture of Rouger in this area. In the second part, I will motivate it by a conjecture of alone around the Ramsey-Cayley graph. We'll study the statistical notion of structure, and we'll talk about Ramsey and random Cayley graph. And in the last part, for the probabilistic discussion, we'll talk about the analysis of sparse random Cayley graphs. With that, let me begin with the first part of the talk, which is about Rouger's conjecture. And Rouger's conjecture is a direct analog of Freiman's theorem, but over a very different class of groups, over the groups that have bounded exponent. So, given an abelian group G, we say that G has exponent R if R is the smallest integer that is divisible by the order of every group element. So the running example that you should keep in mind is just the group G, which is Z mod R raised to the power D. Now, we can ask in this setup, what do sets with small doubling look like? Well, first we do have very easily that the size of the sumset A plus A is always at least the size of A. And in this case, equality can indeed happen. So here, equality will occur even only if A is a subgroup of G. So again, when A is very structured. And so if we look at this question about what are the possible sets A that have doubling bounded to both, let's say by a constant, then we do know a class of examples here, which are just dense subsets of a subgroup of the group G. And as in Freiman's case, we can ask if there are more complicated examples. And Rouger, proving an analog of Freiman's theorem, shows that the answer is no. So he shows that if you take any abelian group G with exponent R, we think about R as a bounded constant. And then for any set A with doubling at most K in this group, A must be a dense subset of a subgroup H of G. So there must be a subgroup H containing A, and the size of H, sorry, this is not equal, this is at most. The size of H is at most some constant depending only on K times the size of A. Now, as in the case of Freiman's theorem, quantitative understanding of Rouget's theorem is an important question that has been studied in many works. In particular, in the same paper where Rouget proved his theorem, he conjectured the correct dependency between the size of the subgroup H and the size of the set A involved in the question. He conjectured that we can take the size of H to be bounded by the size of A times a factor that is roughly R to the order K. And this R to the order K term does not just appear there for no reason. So we can consider this very simple example that already tells us that in this conjecture, we need a term that is at least about R to the 2K. So this example, we work with the group set R to the D, and we take A to C to be the set that consists of 0 and all of the coordinate vectors. So here, the coordinate vector EI has the ith entry being 1 and the rest of the entries are 0. So in this case, you can easily check that the doubling is about D over 2. And on the other hand, A spans the whole group G. So the smallest subgroup that contains A will have size about R to the D. So we see that we cannot have a term that's better than R to the 2K in the statement of the conjecture above. So now let me tell you a little bit about some of the results that we know previously towards Rouget's conjecture. So in the original paper, Rouget proved that we can take here the term that is roughly R to the K to the 4. And later, Green and Rouget improved this bound to roughly R to the K squared. And there are several other results in between, but let me skip to the big breakthrough of Sanders in his work on the quasi-polynomial Bogoliubov-Rouget's lemma. And in this, using the quasi-polynomial Bogoliubov-Rouget's lemma, Sanders proved that we can take the subgroup H to have size at most the size of A times a factor that is roughly R to the K times the polylog K factor. So getting quite close to the conjecture of Rouget. Now into our work, this is still, Sanders' result is still the best bound that works for general abelian groups of bounded exponent towards Rouget's conjecture. But there is a very nice special class of abelian groups of bounded exponent, which are the groups with prime exponent, in particular the finite field vector spaces. So for finite field vector spaces, we know much better results towards Rouget's conjecture. In fact, in 2009, Green and Tao resolved Rouget's conjecture over the group F2 to the D. And later, Evans-Zohar and then Evans-Zohar and Lovett sharpened the approach of Green and Tao, and in particular, they proved this sharp version of Rouget's conjecture over finite field vector spaces, where you can see that we can indeed take the size of the subgroup H to be bounded by roughly P to the 2K times the size of the set A. As the two sets of results suggest, the works roughly come in two different directions. So first we have the more analytic technique, so more or less similar to the route that we would go to prove Freiman's theorem, where we use Fourier analysis and other ideas involved. This technique is very nice and robust. They work nicely over general abelian groups of bounded exponent, but it seems very challenging to push this all the way to the correct linear dependence on K in Rouget's conjecture. On the other hand, over the special groups, over the finite field vector spaces, we have a very different technique, the compression technique coming from extremo combinatorics. And in this technique, what we do is roughly to perform a lot of local modifications to reduce the problem to some nice explicit structured example. We have, however, no control on how many modifications we will need to do. And so for this technique to work, we do rely strongly on the vector space structure. And it doesn't work as soon as we move away from the finite field vector space. And let me note that there are indeed cases, there are indeed phenomena or problems where the finite field vector space behaves significantly different from groups whose exponent is divisible by more than 1 prime. And several of these results exploiting this difference between the two classes of groups are quite important in theoretical computer science. So that let me state the first main result. So in recent joint work with Jacob Fox, we proved Rouget's conjecture in a strong form. So we show that for any abelian group G of exponent R, if A has doubling at most K, then A must be contained in a subgroup H whose size is bounded above by roughly R to the 2K times the size of A. So as we alluded to before, this result would be best possible up to the little o of 1 in the exponent. And as I have alluded to, our proof of Ruja's conjecture is mainly a combinatorial argument. So let me now take the chance to tell you about how we adopt a combinatorial perspective on these additive combinatorial objects. Okay, so this is the combinatorial setup. So first, let's recall what we have in our setup. We have an abelian group G, and we have a set A whose doubling is bounded above by K. Now, we can view this additive input in a slightly more combinatorial way. So first, we can consider a complete graph whose vertices are still identified with the group elements G. And on this graph, we now construct a edge coloring. So we will color the edge between two elements x, y with the color that is x plus y. Now, let's note that this edge coloring, we can easily show that it's a proper edge coloring, which just means that if we have two edges, two different edges that meet at one vertex, they must receive different colors. Now, a set A that has small doubling in the group G will simply corresponds to a vertex subset in this complete graph whose induced subgraph receives relatively few colors. Right, so this is a figure of what the edge coloring looks like in the group Z mod 5. So you can see that there are some self-loops, but for this entire talk, let's just safely ignore all of these small details. We can just treat the graph like a simple graph. Okay, so here comes the surprise, the first time. It turns out that for a lot of what we want to understand about sets with small doubling, we can just take this combinatorial picture and completely forget that the edge coloring comes from the addition on the group G. So this means that we will now work with this more general combinatorial setup, where we have a complete graph. Let's just think about the induced complete graph on the set A, where it is equipped with a proper edge coloring that uses relatively few colors, and these are all of the inputs that we will use from this point. So we'll temporarily forget that this edge coloring comes from the structure of the group G. So within that combinatorial setup, let me now tell you about the key combinatorial lemma. This is one important result that you actually use in all of the three different discussions in this talk. So first, let me define one piece of notation. Given an edge coloring of the complete graph, let me denote n of AB, the set of colors that appear between two vertex sets A and B. So the statement of the key combinatorial lemma looks a bit long, so let us all go along the statement with a figure, just focus on the figure, and I think that's already enough to understand what's going on. So this is the text statement, and this is the better version. So yeah, I'll now go along this statement of the lemma. Let's just focus on what's happening in this figure. So as for the setup, we are given a proper edge coloring on some set of vertices A of size n, and the condition that we are given is that this proper edge coloring uses relatively few colors, at most k times n many colors. There's one technical condition that each color appears not too many times, but we can just safely ignore that condition. Okay, now this is the conclusion of the lemma. We can produce a small set of colors S of size at most big O of k, and in many cases we can make it even smaller, so that using the colors in S, we can create this picture. So we can, using the colors in S, we can partition the set A into these balls Bi, and they will satisfy the following three important properties. So first, the balls Bi, they cover a significant proportion of vertices in our graph. Second, each one of these balls Bi can be connected using only the colors inside the small set S. So it's one common set of colors that will simultaneously connect up all of these different balls across the graph. And the last condition is that if you take any ball Bi, and if you look at any subset A prime of A, which is not too small, then Bi interacts very nicely with A prime, in the sense that the number of colors between Bi and A prime will be already some universal constant times the total number of colors that we have in the entire graph, which is k times n. So roughly, you can think that what this picture is producing is creating, by using this common set of colors S, simultaneously these very nicely expanding structures BI. The BIs, they are expanding and nicely connecting or nicely interacting with any part of the graph, in the sense that in between the BI and every small subset of the graph, we see a constant fraction of all of the colors that we could possibly see. And hope that in some of the applications that I will tell you about later, we'll see why this expanding property is useful for us. So, any questions about this lemma? I think we shouldn't worry about the statement, but just keep some mental image of this picture. So with this, I'll tell you briefly how we can approach Rouget's conjecture given this combinatorial lemma. So the first step, we apply this key combinatorial lemma. So first we translate the problem of a set with small doubling in Rouget's conjecture to the combinatorial language. Then we apply this lemma, which produces for us this picture.
Sorry,
Now,
can I ask, for to get this lemma, the hypothesis is that A has small doubling?
No, so
Sorry?
So you start with a set A that has small doubling.
Okay.
You can translate to a picture like this,
Okay.
where the number of colors is small. But when I get here, I have already forgot that I come from the additive setup. I forgot that I come from a set with small doubling. It's a strictly more general setup.
So here the hypothesis on A is just that A is a subset.
No, so yeah, A here is an abstract set. There's no additive
Just
structure
abstract
on
set.
it.
Okay,
So
okay.
it's just a set of vertices. And the only hypothesis is that we have this edge coloring, and the total number of colors is at most k times n. That corresponds to the small doubling condition.
Gotcha. Understood.
Okay.
Thank you.
Any other questions about this picture? Okay, yeah, so as I said, in this lemma statement, there's no group involved. There's no additive.
Right.
Yeah. Okay, well, yeah, so we start here. Well, we forgot about the group temporarily, but now let's bring back the group structure. So if we bring back the group structure, let's remember that each one of these colors, in our translation between the group theoretic setup and the combinatorial setup, each one of these colors corresponds to a group element, right? And the second property is that, well, what is the set of colors that appear between Bi and A prime is in fact just the sumset, Bi plus A prime. So in particular, we'll use this condition that every sumset Bi plus A prime is very large in order to achieve the next step in our plan, which is the following. So the combinatorial lemma gives us this small set of colors S. Now S corresponds to a set of at most big of k many group elements. Let's let H be the subgroup spanned by these colors. So H is a subgroup with a rather small size. It's spanned by at most big of k many elements. And the key step that we will do here, using the expanding condition, is that if we quotient the set A by the subgroup H, then the set A mod H will now behave essentially like a set with doubling bounded by some universal constant. So we start with a set with doubling K, which is some general parameter, and we have bootstrapped it to a new set whose doubling is bounded by some constant independent of K. Okay. So let me briefly just say how this proof would work intuitively. So, well, if we look at each coset of H, like this one, which contains one of these modes Bi, we know that the sumset of Bi and any reasonably large subset A prime of A will be already a constant fraction of the entire sumset A plus A. So if you assume that the doubling of A mod H is very large, if it's growing to infinity, it turns out that we can prove that we can pack in this joint location many sumsets of this form, Bi plus A prime, inside the sumset A plus A. But each one of these sumsets is already a constant fraction of A plus A. So this will be a contradiction. Right? And roughly that contradiction will imply that the doubling of A mod H have to be bounded by some constant, essentially independent of K. Okay, so the real argument is a little bit more involved and it relies on some other more careful arguments in additive combinatorics, but I won't go into too much detail. Let me just say that once we have the conclusion of step 2, we are essentially done. So A mod H behaves like a set with doubling a universal constant. We can apply any qualitative result of Rouget's theorem that we want. So we can apply, for example, the value coming from Rouget's theorem in 1999. And combining that with the subgroup H we have from the previous step, we'll be able to show that the set A must be contained in a subgroup of the right size. So the last caveat is that I claimed a stronger result, that is resolution of the usual Ruch's conjecture. I claimed a sharp constant in front of K, and in order to get the sharp constant, we'll need to run this entire argument with a lot more refinement and with some additional ideas, but I won't go into that detail. Okay, so, do you have any questions around? Yeah.
Could you say again or give some intuition, why is it helpful that there are many different colors between BI and A prime?
Yeah, so how we use it here was that the conclusion that we want is this statement that A mod H have doubling bounded above by some constant independent of K. So we were assuming that, let's assume that this doubling of A mod H is some little omega of one term, tending to infinity at any rate. Then what we will do is we use some additive combinatorics to show that we can find, just based on the quotient by H structure, many different many sumsets of this form. Like where you take the set A restricted to one coset of H and sum it with some other large subset A prime of A, and we can guarantee that these all have to lie in disjoint location. Okay, but now these are some little omega of one many sets of the form BI plus A prime that we guarantee are to be disjoint. Now, the only assumption that we have is that the sumset A plus A is bounded above by K times A. So if you combine this expanding condition that the size of BI plus A prime is at least some constant, let's say 1 over 10 times K times A, we'll get into a contradiction, right? Because then we can pack at least, let's say, 100 sets of the form BI plus A prime, which we guarantee to be disjoint, into the sumset A plus A, which have size at most 10A, and yet the sum of 100 of these sets BI plus A prime have size bigger than K times A. Is that a better...
Yeah, maybe we'll talk about it later.
Okay, yeah. Yeah, may help if I go into a bit more detail later. So. Right, so there are no other questions around the first structural notion. I'll go to the next part where we'll talk about a more statistical notion of structure for sets with small doubling. So in particular, this will be for some applications to Ramsey theory. Okay, so with that in mind, let me set up some useful terminology from Ramsey theory. Let me say that a graph on n vertices is C Ramsey if its clique independence number is bounded above by C log n, which just means that the graph has no clique or independent set of size C times log base 2 of n. Now, early results in Ramsey theory, in particular the theorem of Additive and Zechariah, tell us that there is no 1/2 Ramsey graph. So every graph on n vertices must contain a clique or an independent set of size at least half times log base 2 of n. So every very big graph must contain inside it a very homogeneous structure. And maybe as many of you may know, there was a quite recent tremendous breakthrough in Ramsey theory by Campos, Griffiths, Morris, and Sahasrabudha, where they improved the theorem of Additive and Zechariah by some small but explicit constant C. Now, let me also remark that there are already several follow-ups to this original breakthrough. Now, on the other side, we have this remarkable theorem of Additive, which tells us that almost all graphs on n vertices are 2 Ramsey. And in particular, there exists a graph on big n vertices for which all of the cliques and independent sets in this graph must have size at most, must have size as 2 times log base 2 of n. Okay. So, let me just tell you briefly, because the proof of Additive theorem is very remarkable. It is one of the first applications of the probabilistic method. So all that Additive has to do is to consider a uniformly random graph among all graphs on n vertices, or in other words, he consider the Additive random graph Gn1/2. Then he consider just the first moment or expectation of the number of cliques or independent sets of this specific size, 2 times log base 2 of n. He explicitly compute and check that that first moment is very small, and hence he immediately conclude that almost all graphs on n vertices do not have any clique or independent set of this size 2 log n. And quite remarkably simple as it is, this has been nearly 80 years, and apart from a quite small improvement, we still do not know any substantial improvement over the original argument of addition. There's also another outstanding problem here, which is to explicitly, either in the mathematical or the computer science sense, construct a C-Ramsey graph for any constant C. Now, if we go along with addition argument, in order to deterministically find a C-Ramsey graph, we may need to search over this huge 2 to the n squared space consisting of all graphs. So maybe a more modest goal, instead of that arriving directly at an explicit construction of a Ramsey graph, we can try to find other distribution on graphs which has much less randomness, which uses significantly less random bit, and still successfully produce for us a good Ramsey graph. So that's one small motivation for us to start looking into this example of random Cayley graph. So for us in this talk, we define the Cayley graph with respect to a fixed finite group G. So over the group G, if we specify a symmetric subset S, which just means that whenever G is an element of S, G inverse also must be an element of S. We can now define a Cayley graph GS will be a graph on vertex set G, and we connect two vertices X and Y if the product X times Y inverse is an element of the generating set S. And given this definition, there's a natural random distribution that we can endow on the space of Cayley graph. So given the parameter P, the random Cayley graph, which I denote by GP, will be a Cayley graph GS, where the generating set S is random, and we simply include each one of these equivalence classes GG inverse to be in S with probability P, independent of each other. So, some motivations for looking at this. Well, this from a Ramsey theoretic perspective, other than the reason that I mentioned earlier, it turns out that all of the few small explicit Ramsey graphs that we know all turn out to be Cayley graphs. In fact, they are a special type of Cayley graph called Paley graph, which I won't define. But Paley graphs and Ramsey properties of Paley graph is an important problem in both combinatorics and number theory, and it seems to be an extremely challenging number theoretic problem. So perhaps we can think about a random Cayley graph as kind of at least a good random analog of Paley graph, for which we can first make some progress on. Cayley graphs and random Cayley graphs are also extensively studied in a variety of places, like theoretical computer science, number theory, group theory, and strong connections to coding theory, especially for quantum codes, and spectrograph theory, and so on. So for us in this talk, the aspect of random Cayley graph that we will focus mostly on in this section is Ramsey theoretic questions. So we want to know what is the size of the largest clique or independent set in a uniformly random Cayley graph. So when the parameter P is equal to 1/2, I will refer to the random graph that we have as a uniformly random Cayley graph. And in particular, we want to know if these guys are going to produce Ramsey graph. And for this one, we are motivated by this beautiful conjecture of Noguera-Long. He conjectured that there is some universal constant C, so that every finite group admits a Cayley graph, which is C-Ramsey. Okay, so for now, it seems like I have been going on a tangent. So we started with sets with small doubling, and so far most of the discussion has nothing to do, seemingly, with sets with small doubling, so let me make the connection back. So it turns out that in analyzing Ramsey properties of random Cayley graphs, the key notion that we look at is essentially just a variant of the notion of sumset inside this more general non-abelian setup. So let me define this product set, A times A inverse, again, just the collection of all elements of the form A times B inverse, where A and B are elements of A. And if you prefer, if you take G as an abelian group, then it's more natural to write in the additive notation, and then this product set will simply become the difference set, A minus A, that we have seen before, and also is of course a close cousin of the sum set A plus A. So why are product sets related to Cayley graphs? Well, a set A will be a clique in a Cayley graph GS if and only if, essentially, the product set A times A inverse, well, minus the identity element, is a subset of the generating set S. So using our definition of the distribution of the generating set S, we can now easily observe that if we want to count what is the expected number of cliques of size T in a Cayley graph GP, this will simply be the sum over all sets A of size t of p raised to a power that is essentially the size of the product set A times A inverse up to a constant factor. And in particular, analyzing the clique number of a random Cayley graph would essentially reduce to the task of bounding the number of sets with a small product set, A times A inverse. So now let me say some of the results that we know earlier in this direction. So there's first a beautiful result alone where it shows that for every group G, the clique number of a uniformly random Cayley graph is at most order log n squared, which is just a quadratic factor away from being random. Now, I will always mention just clique numbers in all of the theorem statements because in this case, the distribution of the clique number and the independence number are actually perfectly symmetrical. So everything that applies to the clique number will also apply to the independence number. This is still the best result that we know that holds over general groups. The only more precise results that we know are over specific nice abelian groups where we have strong structural tools for additive combinatorics. So we have first the result of Beth-Green and later sharpened by Green and Morris, where they show that if the group is a cyclic group Zn, then the clique number is actually asymptotically 2 times log base 2 of n with high probability, which is quite remarkable because this is exactly also asymptotically the clique number of an Eddy-Shreni random graph. And the only other class of groups where we know something more precise is the family of finite field vector spaces Fp to the d. So here we are considering p as a fixed constant. And in this case, Green and Mrazovich show that actually the clique number is going to be of order theta log n log log n with high probability. So quite interestingly, the uniformly random Cayley graph in this case will fail to be Ramsey with high probability. And I'll return to this mystery in a little bit.
Can you just mention, the S is a generating set. That means that it's not redundant. That is, implicitly there was also a choice of generating set for the Cayley graph.
Right.
So in these cases, are you thinking of just plus and minus 1? Is that what is it for?
No,
what is it for Zn? What is S?
Right. So over Zn, we are taking S as a random subset of the group Zn. Right. So it's a uniformly random subset.
Okay. So the randomness is in the choice of the generator. Okay.
Yes. We fix a group, and the random here over uniformly random is over the generating set S. Other questions? Right. So. First result that I will mention in this part is a theorem in joint work with David Coleman, Jacob Fox, and Liana Yepremian. So we sharpen the result of alone that holds over every group G, and we show that with high probability over any group G, not necessarily abelian, the clique number has to be of a uniformly random Cayley graph, will be bounded by order log n log log n with high probability. So in particular, just because of the case of the finite field vector space Fp to the d, we see that this bound is in general the best possible bound that we can prove unless we make further assumptions on the structure of the group G. And as I alluded to, we'll do this by just exactly giving a count on the number of subsets A of the group G whose product set A times A inverse is small, guarded by K times the size of A. And this count is the explicit answer that we get, and let me just remark that this count is in general sharp up to the constant, the universal constants that appear in the bound, and in particular it's sharp over the finite field vector space Fp to the d. And it's kind of a theorem that just tells us that sets A with small product sets A times A inverse are structured in the sense that there are very few of them. And if you look at this statement, again it's a purely group theoretic statement, but once again our proof of this result is entirely combinatorial. So let me make the passage one again, from the group theoretic setup to the purely combinatorial viewpoint. So this will be very similar to what we did for the sumset. So in particular, given any group G, we can consider a complete graph where the vertices are identified with the group element, and we consider this edge coloring C where we associate to two group elements X, Y, the color which is represented by this equivalence class, XY inverse, YX inverse. So you can easily check that this edge coloring is an edge coloring for which each color class is either going to be 1 or 2 regular. So here are some examples of what the edge coloring looks like. in the group Z2 by Z2, it consists of 3 perfect matchings, and in the group Z5, it consists of 2 color classes, each of which is a cycle. Now, a set A with more product set A times A inverse simply correspond to a vertex subset of this graph, whose induced graph receives relatively few colors. And finally, a Cayley graph and correspondingly a random Cayley graph simply correspond to the edge union of some of the color classes in this picture, and correspondingly the random union of the color classes. Right. So now, again, the surprise, which is actually similar to the one before, it turns out that for all of the results that we have mentioned previously, we can forget about the group structure, we can forget about the fact that our edge coloring comes from the group G, and we only keep track of this combinatorial constraint that the maximum degree of each color class is bounded. So this leads us naturally to define this following more general model. So let me consider an arbitrary edge coloring of a complete graph. So again, in this picture, there's no group anymore. And this edge coloring, we assume to have maximum, so that every color class has maximum degree bounded by delta. I'll call this a delta bounded edge coloring. Now let me define a entangled graph. This corresponds to a Cayley graph before. This is simply the edge union of some of the color classes. And the random entangled graph, which generalizes the random Cayley graph, simply correspond to a union of random color classes where each of them will appear independently with probability p. So, as examples, these random entangled graphs generalize Additive random graphs, random Cayley graphs, as well as several other models of random graphs that have been considered in the literature. And in fact, in our later work, we also significantly generalize this family of random graphs to a much more general family that we call delta independent graph, but I won't go into the detail there. So, as I mentioned, both of the results that I've stated over the setup of the Cayley graph would already hold true in this more general combinatorial setup. So in particular, the first theorem on this slide would be a result about counting the number of vertex subsets inducing few colors in a delta bounded edge coloring. And you can see that the bound there looks exactly the same up to this factor delta as the bound on the number of subsets of a group whose product set is bounded. And in the second theorem, we proved that for the random entangled graph, GCFP, the clique and correspondingly the independence number will be bounded also by Euler log n, log log n, just as in the case of a random Cayley graph. So, so these results can address some conjectures in the literature. But let me just perhaps focus on telling you a little bit about how we prove this result, about counting a number of vertex subsets inducing few colors. And so correspondingly, this result is about counting the number of subsets of the group whose product set is small. So it turns out that the main step is a more structural lemma, which says that if we are given any graph on n vertices, together with a proper edge coloring of that complete graph on n vertices that uses relatively few colors, we can then always find a tree which uses very few colors, at most k plus log n many colors, and this tree covers a significant proportion of vertices in the graph. So this result is tight in that if we want to cover all vertices, then you need a much larger number of colors than k plus log n. And I won't go into the detail, but using this lemma, using the tree as a frame to build the set that induces few colors, we can actually easily deduce the bound on the number of vertex subsets inducing few colors. And the last thing I perhaps will mention is that this lemma, again, follows quickly from the key combinatorial lemma that we have seen before. So perhaps let me briefly explain why. So we turn back to this familiar picture of the key combinatorial lemma, where we have these expanding structures Bi interacting nicely with any part of the graph. And note that here we have only used big O of k many colors. So we have log n many colors left. So what we do now, given this picture, is simply in every step, we just flip a uniformly random color. Every time that we flip a random color, each one of these moles Bi will connect to another one with probability at least some constant. So you can track and prove that as we expose random colors, the number of connected components in this graph would roughly decay exponentially. So after log n many steps, we will end up with a giant component that covers almost all of the vertices in the graph, and that exactly corresponds to this tree covering most of the vertices that uses relatively few colors. Okay, so are there any questions around this discussion? Okay, yeah, so again we see this common theme that we can get very far, very close to the, we can essentially the correct answer, while we have not really used almost anything from the group structure. So I will just very briefly mention maybe perhaps this mystery around Alon's conjecture. So Alon conjectured that every finite group should admit a Cayley graph that is Ramsey. So every finite group should have a Cayley graph whose clique and independence number about it are both by some constant times log the size of the group. On the other hand, we already saw that even just over a finite few vector space fp to the d, a uniformly random Cayley graph will fail to be Ramsey with high probability. So given what we know in Ramsey's theory, this seems like a very strange situation. If a uniformly random choice fails, then it's not clear what we can do. But it turns out that in this case, we can slightly alternate the distribution of the random Cayley graph that we have looked at before. And by alternating this distribution appropriately, we can prove indeed that for most of these problematic groups, so over fp to the d for p at least 5, there would exist Cayley graphs that are Ramsey, and in fact they are essentially optimally Ramsey in the sense that the clique and independence number asymptotically matches with the Additive random graph. If p is 1 or 4, we can even show that these are self-complementary, and this is just to address an old question of Alon and Olinsky. Now, this theorem is not specific to finite few vector spaces, so in fact we can build on this result to show that Alon's conjecture holds true in almost all abelian groups. Okay, so just spend a second to say how we modify the distribution of the random Cayley graph. So let's just take the prototypical case of the group f5 to the d. So over f5 to the d, for every non-zero direction, we have two equivalence classes, right? X minus x and 2x minus 2x. So in this distribution of a random Cayley graph, we will introduce some correlation, and we'll pick exactly one of the two equivalence classes to be in the generating set S. The other one will have to be outside of S. So you can show that if you take a random Cayley graph from this distribution, then any set A that has a chance to be a clique must have a very large difference set. And if you combine that input with the previous counting result, then we can actually successfully show that samples from this distribution produce good Ramsey graphs. Okay, so that's all that I will say in this part. So let me perhaps just briefly go over the last perspective, which is in some sense a much more interesting story. We'll now talk about sparse random Cayley graphs, and the probabilistic analysis of these ones are a lot more complicated than dense random Cayley graphs. So, well, in this discussion, it's a bit easier for me to talk about a variant of the Cayley graph called the Cayley sum graph, but it's very similar. Given a group, abelian group G, and a subset S, the Cayley sum graph has vertex set G, and x and y are connected if the sum x plus y is an element of S. So now we can define a random Cayley sum graph just as before. Just pick the generating set S at random where each element is included in S with probability P. That will give us a random Cayley sum graph G plus P. And now we care about the sparse regime. So we want to let P goes to 0 as the size of the group N goes to infinity. You can just think about the polynomially sparse regime. So P is n to the minus c for some constant c. So it turns out that the key challenge here in analyzing the sparse random Cayley graph is that we can write down the first moment exactly as before. So what is the expected number of independent sets of size t in this random Cayley sum graph? It will be some quantity that looks similar to before. So the sum over set A, 1 minus p to the size of the sum set A plus A. But it turns out that this first moment is always going to be too large, no matter how slow p tends to 0. So for example, let's look at the cyclic group Zn. We can easily show that the number of sets A of size t end up being bounded above by some constant, let's say 10, is at least 2 to the t. And just counting over these sets, they contribute to this first moment a quantity that is at least 2 to the t times 1 minus p to the 10t, and this is always much, much larger than 1. So it seems that the first moment method is not going to work, but we do know what to look for in these situations. So we know that we don't have to look too far beyond the first moment method. We do have to look beyond the naive first moment that we considered before. We have to look beyond this quantity, but we can just slightly modify it and look at slightly more general first moment obstruction. And in probabilistic combinatorics, it's several of the recent developments that address this story. So in particular, we know that the first moment is the main driving force in the emergence of structures in very general random discrete systems. This is the content of the Cayley conjecture that I proved earlier with Jin-Young Park. And in fact, there are also very instrumental, interesting related phenomena in probability and geometry. So some conjecture of telegrams that we also resolved. But let me note that these stories only provide half of the work that we have to do. So these tell us that to understand a probabilistic threshold phenomena, we can reduce our task to understanding the so-called first moment obstructions. But in many situations, understanding the first moment obstructions is a highly challenging task. And especially in the ensemble of random Cayley graph, it will be the main challenge in the picture. So let me not say, because of time, I won't go into too much detail. Let me just say that in our situation, the first moment obstruction, which is essentially a general version of the union bound, tell us to do the following. So we have the collection of sets that we care about, which is just the collection of sumsets. We want to build a small collection of sets C so that it covers the collection of sumsets, which means that for every sumset A plus A, there is some set from this family C that lies inside the sumset A plus A. And the smaller we can find such a collection that covers the collection of sumsets, a better bound that we would get on controlling the independence number of sparse random Cayley graphs. So let me now get to some of the results that we have on this line. So first, there are several beautiful works of Alon, and he showed that the independence number of sparse random Cayley graphs or Cayley sum graph is with high probability of order p to the minus 2, roughly up to log factors. And his argument can actually be interpreted as a simple but nice construction of a small cover. Now, what do we expect? Alon makes this conjecture that the independence number of these guys should be with high probability around p to the minus 1. And the motto here is that for global properties like the independence number, the random Cayley graph or Cayley sum graph should behave very similarly to a random Pn regular graph. And the random Pn regular graph would have independence number around p to the minus 1 up to log factor. So now in a recent work with Alon, we improved the previous bound of p to the minus 2 in the exponent to p to the minus 3 half. So roughly halfway between Noga's previous bound and the conjectured answer. And what we do here is exactly to construct a small cover for the collection of sumsets. And let me just say that the main challenge is really just in the case where the doubling is bounded above by some constant. So in fact, there is an open question of Chern-Weil where he just asked to essentially construct a cover for the collection of sumsets of dense subsets A of the group. And if A is dense, then of course the doubling would be bounded above by a universal constant. And so our main technical result fully addresses the question of Lovett. What we do is essentially to construct this efficient cover of the family of sumsets, sets with small doubling. And by this efficient covering lemma, which tells us that there exists a collection of sets C. Each set from C can be constructed using few bits, using at most k squared. The minimum k squared is square root kt many bits. Each of these sets is large, which is helpful for making the cover small, and the collection C covers all of the sumset A plus A. I will not go into much detail now. Our argument here is mainly probabilistic, but interestingly, we look from both the physical and the Fourier space. That's kind of one of the main thing that we have to do in order to construct these efficient covers. And there are several further applications, which I will not go into detail. Let me just quickly conclude. So what we have discussed is kind of a recipe, a combinatorial recipe for understanding sets with small doubling, and roughly it has two steps. So we first have the key combinatorial lemma, this picture, which produces these useful expanding modes BI inside sets with small doubling. And then in many of the arguments that we saw, we will typically apply a refinement step where we use this expanding structure to probe the information about the entire set A that we care about. This leads to some sort of interesting perspective because instead of the usual way of zooming in on explicit structures inside a set, what this combinatorial lemma does is to first provide a template that is as random-like as possible, and that turns out to be very helpful. We just quickly mention that the proof of the combinatorial lemma itself uses randomness that follows from an intricate random exploration process. And this technique, as we saw, can be applicable in wide generality, and it's very good at providing robust structural results, even though I didn't go into any of these details. And let me just end by saying that I think there's a lot of interesting things to continue studying from here. We have all of this monumental development in random graph theory. It would be great if we can bring them over to the theory of random Cayley graphs. Let me note that general results like the Chern-Weil conjecture does work over the ensemble of random Cayley graphs. And essentially it tells us that to understand probabilistic phenomena like the threshold phenomenon over random Cayley graph, it suffices to understand the first moment obstructions. But as we saw in this talk, the key challenge is how we can robustly understand first moment obstructions over this ensemble of random graphs. And perhaps this other nice question, which we get stuck on, I want to tell you, just essentially towards Alon's conjecture, we believe that the main challenge is not in weird or complicated non-abelian groups. We think the hardest case is essentially just the hypercube F2 to the D. And this toy conjecture is necessary to prove Alon's conjecture in this case. And it just asks for a two-coloring of the hypercube where there's no monochromatic subspace that have size too large. They have size C times D. And this question itself has interesting questions to Ramsey theory and additive combinatorics. But perhaps I'll tell you about details later if you're curious. So let me end here.
Thank you. Are there questions?
You mentioned several different constructions of two Ramsey graphs, random constructions. Is there any hope to tweak these to produce a 2 minus epsilon Ramsey graph?
Yeah, that's a great question. So at least for all of the constructions that I mentioned, we do have lower bounds that tell us that we can't improve it to get 2 minus epsilon Ramsey graph. I do want to say this. So if you do not look at the scale of 2 minus epsilon, which is very ambitious, you can look just a little bit better. We do know that the clique and independence number in the Additive random graph is very well concentrated, so typically around just 1 point. And in the ensemble of random Cayley graphs, we can show that the Cayley graph will have clique and independence number actually exactly 1 less than the Additive one. So they improve over the Additive random graph, but they still do not beat the best lower bound that we have on the diagonal Ramsey's number. So yeah, so let's just say that there is hope. So we have kind of briefly looked at this, but if you can find a model like the random Cayley graph, but you can fold in a lot of symmetry. So what helps to get this one additional gain compared to the Additive case here is that the Cayley graph has lots of symmetry, and in particular, whenever you get 1 clique, you can translate it and get n many cliques. If you can get a model of the random graph with enough symmetry that whenever you get 1 clique, you can get some, let's say, n to the k, many other cliques simultaneously appearing. And if you can still analyze the clique and independence number in that case, like in the case of the random Cayley graph, then you can get significant improvement over the Additive random graph, in particular improvement to the lower bound on the Ramsey number.
Any other questions? Okay, no, thank you very much. Let's meet again in 5 minutes.